Hello, everyone. Welcome to the third and last day of the JAX Diffuser sprint. I'm your host today, Merve, who has hosted the 2 previous days with amazing talks from Stability AI, from Google, and from Hugging Face, is on her well-deserved vacation. So I'm Apolinario. I'm a machine learning art engineer here at Hugging Face, and I'll be your host today for the talks by Andreas from JAX and ControlNet, by Boris, and by Meg Mitchell on ethics. So our first talk is from Andreas. He is a researcher at Google on computer vision, and he will be talking to us about JAX and ControlNet. It's a pleasure to have him. Welcome, Andreas. And yes, so yeah, I'm very excited to see what you have cooking. So yeah, I'll leave the floor to you. I will remove my screen and I'll add yours.
Okay, thank you for the introduction, Apolinario. So my name is Andreas Steiner, and I work as a research engineer at Google Brain in computer vision research. And part of my time, I also work on the Flex project that I'll be talking a bit about today. And sometimes I give internal trainings about JAX and Flex to newcomers in research to introduce these frameworks. So I thought today I would talk a bit about JAX and Flex in general. Then I would talk a bit more specifically about how this is used in the ControlNet sprint that we're doing together with some concrete examples. And I also have a bunch of slides about TPU v4s. By the way, if you want to follow along during the presentation or follow up on some of the links later on, I also have a short link here where you can download all the slides together with the links. And by the way, here in the background, what you see, this is not a TPU v4 pod, but instead this is a TPU v3 pod, and there will be some other nice images later on from TPU v4s.
Amazing. Thank you so much. I'll leave you with your presentation.
Thank you. So as I already said, I'll be first talk about JAX and Flex. And because there has already been a talk about statefulness in JAX, I'll really mostly concentrate on JAX in this first part. And this will also be the largest part. And then the 3 other parts that come later, they'll be a bit smaller. So first, JAX and Flex. With JAX, there's really like one small weird trick that can significantly accelerate your computations. And a bit later, I'll show you a second trick that will make it even much faster. So the first trick is very simple. Instead of importing NumPy as NumPy, you import NumPy from JAX as JNP usually. So often we have JNP as JAX.NumPy. And at the same time, in the same programs, you also have NumPy as NP. And this allows us to control which of the computation we want to have on the host using NumPy. And most of the computation will be done on the accelerators using JAX NumPy. And you can see here, we do a matrix multiplication, 5K by 5K, which takes around 10 or 11 seconds on a single CPU core. And if we do the same computation using JAX.NumPy, this will automatically be moved onto a connected accelerator, so a GPU or a TPU in this case. And we have a significant speed up of like around 2000. You can also see in this case, if I want to time some computation like here, I would not only do the matrix multiplication, but I would also add this block until ready. And this is because all the computations in JAX, they're asynchronous by default. And I also talk a bit more about why this is the case and what we need to consider when we deal with asynchronous computations. And before I introduce some of the other nice features of JAX, let me speak for one slide about higher order functions. And here, actually, in most cases where I talk about functions, I really mean a pure function. So this means that the return value depends solely on the input arguments, and there's no side effect going on. So, whatever this function would do that doesn't result in a change of the return value based on the input arguments, we will not consider it. So a pure function wouldn't have any of those other components. Okay, so this is a single or a simple classical function. And now if we have a higher order function, like for example, a function transformation, this looks similar to the example up here, but now the input arguments and the return value, they are functions themselves. So in the case of a function transformation, we might take a function as an input, and then we might return a transformed function that does something different. But in this case, it would have the same input and output signature. And of course, when we do a function transformation, the input and the output signature, they can also change as part of the transformation. So let me illustrate this with a small example. Imagine we have a single or a simple function called add that simply adds together two tensors. And then we have a very simple function transformation that takes a function as an input, and it returns a function that basically has the same input and output signature, but in this case, the return value will only be half of the value that would have been returned by the function that is a parameter to this function transformation. So if we, for example, call this add function with 2 and 4, we will get a result of 6. But then if we first function transform the add function with this half function transformation, this expression here, this will return a new function. And then in the same line, we execute this transformed function. And we see that the return value of the transformed function is indeed only half of the return value of the original function. These function transformations, they can also be composed. Like here we apply half twice on the original function add. And what you will also often see in Python is that these function transformations, they're simply being written with the decorator syntax. So here, the function transformation half, we would simply prefix it to the position where we define our function with the add symbol. Yes, so what can we use these function transformations for in JAX? A first example would be the VMAP transformation. Imagine here that we have a function, simulate, that takes some position and momentum as input parameters, and it expects those two parameters to be scalar values. But now we would want to do a computation of this simulate function for a whole vector of momenta and a whole vector of positions, evaluating this expensive function for each of the combinations of position and momentums. So of course we could write this as a simple nested Python loop, like what I do here. But the problem with this is that all the computations, they will happen sequentially, and which is a problem especially when you use accelerators. All these computations, they will happen like one by one, and there's no potential of getting any benefit from vectorizing the computation. And in this case, we take JAX.vmap to the rescue. So instead of doing a nested loop, here I would take the function simulate and then first JAX vmap transform it. And so this simulate here, it will now contain or point to a transformed function. And this transformed function is vectorized along axis 0 in the first argument. So this would be the argument position. Then I can take this transformed function and transform it for a second time. So here I compose this JAX vmap transformation, and this will yield a new function that is vectorized both in the first and in the second argument. And then I can call this vectorized function a single time with this vector of momenta and positions. And now this vectorized function, it will take full advantage of the vectorized computation that's possible on hardware accelerators. And this will result in a computation that's a lot faster. A second interesting function transformation that is very relevant for machine learning work is the GRAD function transformation. And GRAD stands for taking the gradient, or autograd. And JAX is actually a recursive acronym of autograd and XLA. And XLA is exactly the second trick that makes the computation faster, that I'll explain a couple of slides later. So imagine here that we have a function that computes a scalar loss given weights, inputs, and targets. Now I can transform this loss function using JAX.grad, and this will return me a function grads, this expression here will be a new function. When evaluated with weights, inputs, and targets, it will return the gradients of the value returned by the original function. So it will return the gradients with respect to the loss, or of the loss, with respect to the first argument, which is the weights here. So grads will have the same shape as weights, but every value in grads will be the gradient of the loss with respect to this weight. And then in a typical machine learning program, we would use it like this, that we have the loss function. Then we have an update step function. And in the update step function, we first compute the gradients. Then we take a small step against the gradients, and we return the updated weights. Now you can see that this update step here, it's still a pure function because there are no side effects. And this is opposed to the code that we have down here, because here we have a data iterator, and we iterate through this iterator. This will mean that we update the state here, and also when updating the state, we usually fetch data from network or from the hard disk. So this is classical side effects that we couldn't JAX transform. But inside this training loop, we have the update step that is a pure function, and we'll see later that this update step can be function transformed using JIT or PMAP. At this point, you might be wondering, how can JAX analyze your functions and then transform them? And this is what I will explain to you in the next couple of slides. At a high level, we have Python code, and then we use JAX to trace this Python code, which will yield a JAX-spur. This JAX-spur can then be manipulated or transformed by Python code, and we can trace this transformation again and go around in the circle. And that's exactly how we can compose these function transformations. So let's first look at the tracing. Sorry about that. Yeah, so let's first look at the tracing. So we have a mathematical function here that would take the logarithm on the basis of 2. And we can write this in Python code where we take the logarithm and then we divide it by the logarithm taken of the number 2. And now the tracing is the process that takes this Python function here and then transforms it into a JAX-spur. And you can see that JAX-spur is simply another way of describing this original function you have on the left side here. The big difference between Python code and JAX-spurs is that Python code is very powerful, and it's also difficult to analyze because it's so powerful. For example, we could overload this division operator here, and inside this overloaded division operator, we can do arbitrary code and arbitrary side effects. On the other hand, if you look at the JAX-spur, this is simply a list of simple equations with inputs and outputs, which makes it, a lot more like restricted in terms of what it can express, but it also makes it a lot easier to analyze and transform. So if you go a bit into more detail how exactly this tracing process happens, first observe that the atomic or like the primitive computations that we do, we import them from jax.lex, which gives us a set of, a restricted set of these primitives. And then when we trace the function, so in this case, we look at the forward Jacobian transformation, we would call our function with a value of x, and x in this case, it would be a vector of size 2 with 1s. And what happens now for the tracing is that JAX will look at this value that we provide here, and then it will create a tracer object. And this tracer object, it will contain, in this case, the shape and the data type and also the value of this x that we provided, but then the tracing object can be observed how it interacts with other tracing objects and how it interacts with JAX primitives. So if you walk through this function here on the left side, we'll see that for each of the operations, the tracer object observes what happens with it, and JAX will note a corresponding line in the JAX-spur. And this way, by simply analyzing the interactions of the tracer objects with these JAX primitives, we get to the full JAX-spur that is the equivalent of the computation we do in this Python function. And now the second step is we do a function transformation of such a JAX-spur. In this case, I'm looking at the Jacobian vector product, and this is a way how we can compute the gradients of a function. And first, one important point for such a transformation is that all the underlying JAX primitives, we have a rule for them. And in this case, or let me maybe make this semi-transparent here, because the internals, how this works exactly, is not so important. The important part is simply that we have a JAX-spur, then we have some algorithm that processes this JAX-spur equation by equation, and we can transform these equations because we have rules for the underlying equations, and then we can algorithmically transform this JAX-spur. And in the end, we can execute this code with a JAX-spur and some concrete values as input. And in this case, it will compute the gradient for this given function here. And now, and this is kind of the, the important point about transforming or about composing these transformations. Since this is simply Python code, we can again trace this by providing traces for the values of the concrete values here, x and t. And if you do this, we get to a new checkspur, and this new checkspur is now the transformed checkspur that we had as an input here. And because this is a checkspur itself, we can now continue this cycle and take the checkspur, apply different Python code on top of it that transforms the checkspur, trace the execution of this Python code, and get to a new checkspur. So this is how we transform or how we compose these transformations. And at any moment, we can use the Python code to compute the actual evaluation of such a checkspur or a transform checkspur. Or another thing we can do is we can look at the checkspur, which represents our entire transform computation, and then we can compile that checkspur using XLA. So consider, for example, this simple function here, where we add two tensors, x and y. And now imagine that one of the tensors is a matrix and the other is a simple vector. So if we want to compute the output of this function, we'll see that first we'll need to broadcast the vector to a matrix form, and then we can add these two matrices together to get to the result of the function. Now the problem here is that if we do this step by step, we might have a lot of memory transfers. So XLA, and XLA, by the way, stands for Accelerated Linear Algebra. So XLA will analyze our computational graph, and it will identify such blocks where we have two individual computations that can be fused together. And fusing together really means that we will stream through the y or through the values of y and x and keep them in registers to perform the entire computation. So we don't have to take the intermediate results and store them back to memory. And this has benefits because when we do this in a streaming way, we will have the same computation, but fewer memory transfers. And memory transfers are very expensive, which might considerably slow down our overall computation. And this way, we will not achieve, the maximum number of flops that would be possible on a given platform. XLA can also do some other things when optimizing this computational graph, like, optimizing the memory layout, or it can do rematerialization, where we can trade some compute for memory or the other way around, or it can even, strip large parts of our computation because we don't depend on them for computing the output values. So why this lengthy explanation of how JAX works and what we can do with them, with XLA on these checkspurs in the end? This is really to introduce the JIT, or actually I already mentioned it here. So here, it's the JIT function transformation that will call or that will use XLA to transform your checkspur into an optimized version that will be executed on the accelerator. And this is really what you will do later on. You will define a function like this function here, which computes the square of a provided value. And then you will apply JIT on this function to compile it and to execute it on a GPU or on a TPU. And there are some sharp edges when you do that you need to be aware of. And one is that these functions need to be pure. I already mentioned this a couple of times in the presentation, but this is a really important point. So imagine, for example, what happens when you have a print statement here. Now we know that when JIT wants to compile your function, it first needs to trace it. We also know that the output value will not depend on this print statement. So this print statement will not be part of the checkspur. And we also now know, because we know how tracing works, that when we call JIT of square, nothing happens at this moment, but only later when we execute this JITted version, providing a specific value here. Only at this moment, we will have the data type and shape available that we require for the tracing. And when we do the first tracing, we will see this print statement as a side effect. But because this print statement is now not part of the checkspur that represents our computation, when we do exactly the same statement for a second time, then we already have a compiled version of square, a JIT compiled version of square. So we will use this cached version. And this time, despite we have the correct output result, the side effect will not be executed for a second time. By the way, if you want to do things like a print statement, during the computation, where you also have access to the values, you can use JAX debug print, which has a similar, function, or like a similar function to the original print. And by the way, another thing is also, it's fine to use any kind of state inside the transformed function, but you should not depend on state that goes across these function boundaries where you apply the function transformations. A second important part is to understand how control flow works inside these functions. Imagine that here we would want to implement a multiplication by unrolling it in a Python loop. Now, if you try to JIT compile such a function, you will get this somewhat cryptic concretization type error. This concretization type error really means that at this position here, where you look at the value of n, this value is not available. And it makes sense that this value is not available because we want to JIT compile this function to work with any values. So when we JIT compile it, the actual value of n will not be available. And that's also why this Python control flow here cannot be unrolled, because we don't have a concrete value for n, and this is what creates this error. On the other hand, it's fine to do control flow that's dependent on the shape or data type, because in XLA, every time one of the input arguments has a new shape or data type, we need to recompile the function anyways. So the shape and data type, they're known at compile time. If you really want to implement the function like here on the left side, you could do this by specifying static argnums. And static argnums would really mean that every time we recompile, or every time we execute this function, if n has a new value, we would recompile it. So this way, the cached compiled functions will have n as part of their cache key effectively. A second option would be that we use XLA control flow from the jax.lex package. And this way, we wouldn't need to trace this while loop anymore, but the while loop would be expressed as, as a jax.lex primitive. And this can later be translated directly to an XLA instruction. A last sharp edge that I wanted to mention here is that all computation in JAX happens asynchronously. So if we have some expensive computation, like for example here evaluating a model, when you call the JIT compiled version of this, so here we have outputs equal, the output of this function, the Python code will continue running here even though the computation is not finished yet. Now what happens when you print, for example, the shape of the outputs, because the shapes, they're already known, this will also happen asynchronously. So this print statement, it can happen while our outputs are still being computed. On the other hand, if you want to print like the actual values of the outputs, at this moment, your Python thread would be blocking until the computation is finished. And that's also something that's important to be aware of, because, for example, in your train loop, if you print the loss, and the loss is returned by your update step, and you do this in the same thread, then your computation would be blocked at this moment until, or your Python thread would be blocked until the computation is finished. And if you do this, then you lose the benefits of being able to do Python code, like iterating through your data set, at the same time that you could do the computation on the accelerators. So this async computation is a simple way of using single-threaded Python programs that do input processing in Python at the same time as the computations being done on the GPU or TPU. Yeah, I've already mentioned accelerators a couple of times. And of course, one thing you can do to accelerate your computation is to use a more powerful accelerator. And we can use jax.jit to make good use of these powerful accelerators. Another thing you could do is that you connect multiple accelerators to your computer. And if you want to do this, we will use the pmap transformation. You remember from earlier that we had this vmap that takes a function and transforms it so that the transformed function can take a whole batch of input elements. Like here would be a single element, returning a single element, and here would be a batch of elements and also a batch of elements that's returned. Now we can replace vmap by pmap, which has a similar signature to vmap. And if we do this, then the computation will happen on parallel on all the attached devices. One important difference here is that pmap expects that the shape of the input values has a leading axis that is equal to the number of attached accelerators. And you see here that if you have a batch of n values, we would usually reshape this batch to first have a dimension of d for the number of devices, and then a dimension of n divided by d. And now also each of the device would only see this part of the shape here. So the first axis, that is per number of devices, this disappears during the computation because the computation happens on these devices in parallel. In one of the last slides, I also show you a different way how you can perform the same thing using the updated JAX.JIT. And now 2 slides about Flex. And Flex is really a neural network library for use with JAX. And you might have heard about Haiku also. And Haiku is, has exactly the same function as Flex for constructing neural networks. And Haiku is the library that's mainly used inside DeepMind, and Flex is the library that's mainly used inside Google. But you can also use both those libraries at the same time and combine them. Then there's other libraries in the JAX ecosystem, like Giraffe for computing neural network or for computing graph neural network libraries, Optax for implementing optimizers, or Diffrax for computing differential equations. And the point of this slide here is that, opposed to some other frameworks, like for example TensorFlow, JAX is simply the base framework unifying everything. And then there's a lot of smaller modules on top of this that can be used interchangeably, and they all use JAX for the computation and interoperate through JAX. You'll also see that some parts that are important for machine learning, like for example data loaders, are not actually implemented as part of JAX. So in this case, we would be using TensorFlow datasets or PyTorch data loaders. And in the case of the control net, the script that we provide you with, we are using the PyTorch data loaders for the input preprocessing. So let's look a bit in more detail at Flex. And, there was an excellent talk by Sabrina Milke on day 2 of this sprint. So I highly recommend you watching this talk, where Sabrina goes into a lot more detail about how state is handled inside JAX frameworks. And there's also a great documentation from Flex that goes into more detail of the module lifecycle. And if ever you run into surprising behavior with Flex modules, I recommend you also having a look at this documentation here. But you can see in a nutshell, Flex is a way that allows you to define your neural networks with very little code. So for example, here we would define a multi-layer perceptron by instantiating 2 dense layers and applying a nonlinearity in between. So Flex really helps you with state handling, and it provides you with predefined layers, like this, this linear layer here. But we also have more complicated layers, like for example, self-attention with autoregressive caching. And you can also see that the state handling, like for example, what happens to the parameters of this NN dense, this is handled by Flex in a transparent way. So you don't need to carry around these states every time that you use such a module. And another thing you can see is that here we have a single function that both sets up our modules and then also applies the forward path. And this is very beneficial when you have more complicated modules, because often you'll have some control logic for the setup and then for the forward pass. And having this in a single function allows you to deduplicate this logic. Another thing that you see here is that you don't need to define the input shapes, or you don't need to define anything based on the input shapes when you define your modules. And this is because we have shape inference, and these internal shapes, they'll be determined the first time that we call this module with some actual input data, which will define all the input shapes. So this is what your code would look like when you define modules. And now it's important to understand, if you want to use these modules in a JAX program, you'll be calling them through these 2 functions, model.init and model.apply. And these 2 functions, they're pure JAX functions. So this is the difference to the function here, right? Because here we instantiate this dense and then we apply x, or we compute the output value given x as an input value. But in this function here, we don't provide any state, but the state instead will be handled by Flex behind the scenes. On the other hand, when we're in stateless JAX land, we need to provide the state to each of these functions because these are pure functions. So the important thing to understand here is that when you call model.in or model.apply, then Flex internally will set up a couple of things such that you can then use this code inside your modules, even though this is not pure functions anymore. Okay, with this, let's get to the control net example. And the first thing, and this is, by the way, the entire code of like our training script that we're using for this sprint. So the first good news for you is that there's actually very little JAX Flex specific code in this example. And most of the code is really about input processing, interfacing with Hugging Face Hub, or sending metrics to weight and biases. So very classic like machine learning code that you, even if you haven't used JAX and Flex before, are probably already familiar with. The two parts that are a bit more specific to JAX and Flex is first the train step here, and then second, the train loop down here. And for the train loop, we prefer usually in JAX not to have some abstraction like TensorFlow Keras or PyTorch Lightning that would take control of our training loop, but instead we would prefer to write out the training loop, because this makes it a lot easier to change things through code instead of changing the behavior through configuration. But it also makes that you have some more like lines of code in your example that implements the actual training loop. Yeah, so the train step, I already told you before that we would try to take the largest possible pure function and then JIT compile this large function. This is also why like this largest possible function is usually the function called train step. And you can see here that everything you want to change in the train step, like the state that contains the optimizer state or the parameters, or also the random number generators that we use for generating randomness, for example, in the diffusion process. All these things that are changed during the training step, we need to return them from the train step. So you can see here that some of these parameters like state and train RNG, they're both input arguments and return values. Inside the train step, you would see that we have a compute loss function. Then we take the gradient from this, and then we apply the gradients to the state. And if you look inside this data class that is state here, you'll see that we use the gradients to compute the new optimizer state and then to compute the updated parameters. And you see here also that when we use this pattern of updating a data class, where internally the data class is updated with self.replace, we would then take this return value and store it as new state. And this new state is what would be returned from the train step. And then in the main loop, we would keep updating this state that is contained in this variable state. And then, in our example, we have multiple accelerators. So instead of JAX.JIT, we would use JAX.pmap. And now an interesting thing when you use pmap is that all these state variables that you have here, we need to replicate them manually. So you'll see in the code that we use this JAX.replicate. And you'll also see if you want to do something with return value, we'll usually call unreplicate on the return value, so that you would get one of the copies from these multiple devices that are attached. Yeah, a final slide about what we do in the control net example is for setting up profiling. I think this illustrates two things that I said about JIT compilation and asynchronous processing. So the first would be if we want to profile our train step before starting the profiling and before ending the profiling, we would make sure that the previous computation is finished by calling block until ready on one of the return values. A second thing that's important to consider is that we would never compile the first step, but we would only start at global step equal to 1. And here global step is incremented starting at 0. And this is because the train step, if you go back here, we pmap the train step. So this means it will also be JIT compiled. And this means the first time we execute the train step, it's at this moment that the JIT compilation will happen. And if we already started the profiling at step 0, then we would profile the entire JIT compilation, which would create a lot of additional events that are not so interesting for our profiling purposes. Yeah, with this, some words about the TPU v4 platform. And everything that I tell here is from this paper that has come out just a couple of weeks ago. And if you're interested into the technical details, then I highly recommend reading up in the paper. So the first thing that's important to understand is that we have these really large pods, and in this case, one pod is equivalent to 4,096 chip, and these chips they're glued together on a single PCB where we have four chips on one PCB. It's also one of these boards that will be attached to a single computer, which you will control as part of the sprint. But now the slightly confusing thing is that each of those chips contains two cores. So we have 4,096 chips, but the double number of cores on those chips. And now there are two different configurations. You can use these cores individually, or you can, like XLA, can treat them as a single device, in which case you will only see 4 attached devices. And this is exactly the configuration that we use for our sprint. So when you call JAX device count, you see the number 4, even though when you create such a VM, the topology will be called V48 because we have 8 cores on such a configuration. A second thing that's very interesting with the TPU architecture is how these chips are interconnected. We have a very high bandwidth intercore interconnect, and this intercore interconnect is arranged in a 3D pattern so that each of the chips has a connection to 6 neighbors. And now we have these small cubes with 64 chips in them, and if you want to connect these, and actually these connections here, they're hardwired, but if we now want to connect these cubes to a larger topology, we will use optical circuit switches for this. And the beauty of optical circuit switches is that we can rearrange these smaller cubes in a flexible way. This allows us, for example, to have a toroid, or like a configuration like a torus, or it also allows us to have another configuration like a twisted torus. And these different configurations, they are optimal for different communication patterns, which can be optimized for different computational workload that you have. So as I said before, there's like much more details about the TPU architecture in this paper if you want to know more. With this, we already made it to the end. And, because most of this talk was more geared towards people who are new to JAX and Flex, I thought I would also mention a couple of features that are more recent for people who are already very familiar with JAX, so they can also see some interesting new things coming up. The first of this is that since JAX 041, we actually have a new distributed JAX.array interface. And using this JAX.array interface, for example, allows you to, to rewrite your code that is using PMAP in a nicer way, among many other things. I mean, the main advantage of these distributed arrays is really for model parallelism, but because that's something we didn't touch on in these slides, I'm going to illustrate it with a PMAP example. So what we have here on the left side is a computation very similar to the one that I showed you on an earlier slide, where we apply PMAP, and we need to manually call replicate before calling PMAP. And with the new JAX arrays, you can actually take the input arrays and then apply a sharding to them. And then you can simply call JAX.JIT on the train step. And you don't need to replicate your inputs and outputs anymore, but JAX will do this transparently for you. So this is like a nicer way of writing the PMAP, but it's also a much more powerful way of writing your program for model parallelism. A second thing that's been introduced recently is the shard map transform. And the shard map transform basically allows you to retain some manual control when you use pjit that does, like most of the heavy lifting for you automatically. And you might be wondering why you would want to have some manual control over these things. And if you want to know the details or like an illustration of one of the cases where this can be beneficial, I recommend you have a look at this paper. And here's just some code that basically shows you how you could apply shard map for computing, for doing a model parallel computation of a matmal. But we don't really have time to go into the details here, but if this looks interesting to you, then make sure to have a look at the SHMAP documentation that has this example in more detail, and then also a bunch of more advanced model parallel examples. And finally, since recently, JAX also supports integration with Triton, and there's like a dialect called Palace that allows you to also use Triton with JAX transforms, essentially. But also here, that's more kind of a name dropping for people who are interested in Triton, so that this is implemented in JAX as well, with 2 links to follow up and read more about this. Yeah, with this, we're at the end of the presentation, and I'd be happy to answer any questions from you.
Thank you so much for your presentation, Andreas. This was really informative. And yeah, we have a few questions in the chat. I will select 2 maybe for the interest of time. So we have Alex McKinney and Kamenduru with quite a few questions. One of the questions that I think it's interesting here is from Alex about the topology. So he's asking, what is the topology for smaller TPU pods? Say 4 like we have in the Sprint. So for those who don't know, in the Sprint, we'll be giving some TPU v4s to the participants. If you were interested in that and you haven't joined yet, feel free to go to the live stream on YouTube video description, and you can see a GitHub link with the instructions. But yeah, so this is the question from Alex. What's the topology for smaller TPU pods like the 4 we have in the Sprint?
Yeah, that's a great question. So that's exactly what we see here on the left side. So during the Sprint, you'll have one of these boards that is attached to one computer. So you will have these 4 chips with 8 cores, but because the way how these 4 chips are configured, you won't see the cores individually, but you'll instead see only the 4 chips as like single cores. But it also means that each of the cores has like double the compute and double the memory of a single core. And these, they will all be directly connected through like an interface with the host computer, and they will have connections between each other. So for example, in our Sprint code, when we call the jax.lex.pmean, then the gradients, they will be averaged directly by the connections on the PCB between these 4 chips, and they don't have to go forth and back to the host.
Awesome. Thank you so much. And yeah, Kamenduru had a similar question that I think you answered in this, which he was asking, why are we getting 4 for JAX device count and not 8? But I think that's what you just answered. And the same question or a similar question is, how can we use all 8 cores?
Yeah. Let me just reiterate here. And you do have the 8 cores, but XLA like fuses 2 cores together each. So you only see 4 devices, but you get the full compute of the 8 cores. So for example, if you wanted to split these cores and have 8 devices, then each of the devices would only have half the compute and half the memory. So this wouldn't make your computation faster, even though you have double the number of cores. And in our example, because we have fairly large models, it would even be like not a good idea, because you would have half the memory. So the model wouldn't even fit with the same batch size anymore in this case.
Yeah, and then one last question before you wrap is, what's the total memory size for the device that we got?
I always like mix. I think it's 32 GB for the 32 or 64, depends on. Yeah, I always mix those 2 up, but I'll check afterwards and I'll reply on Discord.
Perfect. And yeah, and then also in the Sprint details, we have all the information there for the people participating. So yeah. Well, thank you so much, Andreas, for your time and for this amazing talk. And I hope to see you soon. Bye.
Bye.
All right, everyone. So now we will have joining us Boris. And Boris is the creator of DALL-E Mini, which is the first text-to-image model to go really viral. And for those who don't know, this is actually started in a sprint like this. So in 2021, there was a JAX sprint with Hugging Face, and that's the first DALL-E Mini version emerged from one of the sprints. So this is going to be very exciting to me and to everyone here to hear a bit of the story, the developments, and what's next for DALL-E Mini Cryon. And so welcome, Boris.
Hi, everybody. So thank you for the introduction, Apollinario. So I'm Boris Teima, and I worked on DALL-E Mini during the first JAX event as as I was introduced. So as you see, like on the middle, it's actually the icon that we had for DALL-E Mini. This is actually, I don't know if you recognize, but it's supposed to look like an avocado armchair. That was like a very important illustration done by the original DALL-E by OpenAI. So we were like, let's try to generate it, and we had that cute icon. So like that's a cool logo to have, and now it became Korean. So it all started with this event, and now it became like a website that a lot of people use all the time. So it's quite exciting to see like how these products can go by starting with the JAX Hugging Face print, and now like having so many users. So I'm gonna try to tell you a bit about the story of how it happened, how it evolved, and hopefully give you a bit of inspiration for your event. A lot of these things apply for you too, even though you're gonna work more on a diffusion model. But I'm gonna try to keep it a bit general and give you practical advice. So quickly, what is DALL-E Mini? DALL-E Mini is a simple model that basically you type text and you get an image out of it. So one of the first fun one that we had was the avocado armchair. The one you saw initially looks a bit different because I think the prompt is actually logo of an avocado armchair. This one you get the full real avocado armchair. It looks pretty cool. I think like the here it doesn't look pretty comfortable for your back in some of them, but otherwise they look pretty cool. What's interesting with this is like initially it started with very simple prompts, like we were maybe just drawing view of the beach and we're happy. And then we became a bit more creative as the model was working. And for example, here I have the Eiffel Tower landing on the moon. But then at some point, we grew the model. It became DALL-E Mega when it went to a much larger size. And what was interesting is people were able to do very creative prompts. So I really like that one. That's one of my favorite. Teddy bears thieves in a store CCTV. And it really looked like teddy bears you can see like robbing a store. And what's interesting about this model, I think, is like the quality is not as high, but the information is so well compressed because we wanted just something that works. So there's not too many tokens and all, and I think somehow it's still one of the models that's able to do the craziest things. So you can type very interesting prompt. Maybe you don't get the best quality based on what you would have nowadays, but you get that kind of stuff that you cannot get anywhere else. And to me, it's still amazing. Like how did it even draw something like that? It's still a bit magical, even seeing it working. So quickly about how did it start? There was that OpenAI paper about DALL-E. At the time, you couldn't test it, but they had a few cool illustrations, and they had a lot of interesting technical details. And I saw that tweet about, with an example, an illustration of a baby daikon radish in a tutu walking a dog. And you had those illustrations of a little radish walking the dog. And I thought, wow, that's really amazing. And I was, okay, I want to learn how to build it. By the way, this prompt is still crazy hard to do. Even if you try on DALL-E 2, it doesn't work as well. It doesn't work really well at all, to be fair, in any of the diffusion models I've seen. So it's quite interesting. I actually, on a side note, I wonder if, the diffusion model versus like the autoregressive models, which are like DALL-E Mini and DALL-E 1 are able to do more complex things in some ways. So 6 months later, more or less, Hugging Face organized that competition. And when I was like, I want to learn how to build that, the first thing I did, I opened the paper, I opened the blog post, and it was really, really hard to understand. It was very complex, and I think you need to not be too scared about these papers. Some of them, like the DALL-E paper, I probably read it more than 50 times. And each time I go through it, I'm sure if I open it again right now, you see something different and you learn something new all the time. And then you have those references to other papers, and you cannot be scared of going through it. Still nowadays, there's a lot of paper I don't understand, but you need to go through it. So the cool thing about it is like you get in this event, you get to learn how to use JAX flags, which is really cool, which probably many of you have never used. It's different from PyTorch, but in the end, when you build a model, whether you build it in Keras, PyTorch, JAX, there's a few differences, but most of them work the same way. You have layers pre-built for you, dense layers, convolution layers. You stack them, and there's a few differences. JAX is a bit more different in some ways with the stateful versus stateless abstraction. But in the end, you can learn it, and you see it's quite magical and quite interesting. What is cool in this event, you get also support from both some Google engineers and Hugging Face engineers, which is a really nice opportunity. So I definitely recommend you to join it. And the last piece that's really cool is you get access to those TPU VMs. It's quite addictive. At the time I thought I had a pretty cool computer. I had a NVIDIA 2080 Ti, which is pretty nice. But it's no match to the TPU VM. So take advantage of it, play with it. You quickly get addicted. So when I saw that, I immediately posted the idea to do a DALL-E project, and I like to read it because it's fun. It's like, it would be cool to recreate something like DALL-E. I can see some challenges though. Difficult paper, the main concepts could be simplified. Availability, collection of dataset. The model used was GPT-3. Not sure if interesting results can be obtained with smaller models. Actually, it's not correct. It was not GPT-3, but it's kind of the same architecture, I would say, that they had. It may require more time to implement. Remember, it's actually a short sprint in the end. And also, I don't believe a public version is available, so maybe it will be easier to just do it in PyTorch. I have no experience yet with Flax JAX. So when you look at that, that looks kind of scary, I think. Somebody proposing that project. What's funny is actually a bunch of people decided to join me. Like, yeah, great idea, let's do it. And what is fun is that we actually did it. So it's pretty nice. We had a very tight timeline. So from the project proposal to the demo submission, there's about only 3 weeks. And the first part is just trying to figure out how to do it. So it's quite interesting. It's those are very ambitious projects. I think in these teams, you need to have a few project management skills. You're going to work with other people. It's important that you keep yourself updated all the time. List the task so that people can organize themselves. And what's important is there's a lot of tasks that can be performed simultaneously. So for example, preparing the data set, preparing the demo, maybe there's some sub pieces that can fit together, and it's important to do that and see how people can organize themselves around it. What will happen is because it's all a team of volunteers, people self-assign some tasks. I would say, it's normal that some tasks are difficult, you may not succeed. Be open, talk about it within your team. What's important is you need to have a bit of accountability. If you say, I'm going to take care of this part and nothing happens and people depend on you, please be mindful on that. Some members are going to be more involved than others, and it's okay. What is interesting is it's a marathon, it's a sprint, but I think, it's interesting to join because at the end you can learn something, and you will probably learn a lot, and it will be a very unique experience. So it's very fun. Something that you should start with when you have your idea, try to find the papers that are relevant to your problems. So we read a lot of papers, and we read them many times. So those are the 3 most important papers. The zero-shot text-to-image generation for us was the DALL-E paper. Taming transformers for high-resolution image studies basically was mainly what we used was mainly our image encoder, which came from that paper. And BART is about sequence-to-sequence models. So it's kind of a basic paper in the end. I mean, not basic in the sense that it really applies to any kind of model that transforms a sequence to another sequence. But we went back to this paper because you can learn some concepts that are going to be important. So don't be scared about revisiting simple things. I think I was revisiting even the transformer architecture many times. So go back to that. You don't have a lot of time, and it's important to leverage the open source ecosystem to build your prototype. Fortunately, there's a lot of code that you can use. So the first thing is like finding the data set that can be appropriate. Maybe you can build some, maybe you can start with something that will work and then try on yours. It can be a point of failure. At the time for us, we had conceptual captions and YFCC that were applicable. Nowadays, there's a Lion, has a lot of really cool data sets. You don't have to download it all. You can download based on the memory you have. Only 10 million examples or less can be sufficient. 10 million seems like a big number, but it will fit easily on your memory. Also, at the time it was a bit hard to download. You have to figure that out. So maybe you can have a member to find out how to do it. So the library to download image dataset that I like a lot is img2 dataset. It's really nice because you give your list of data that can be in a lot of formats, and you can output it in a lot of different normal, whether web dataset, TF data, or just files. So something else is like, it's good to use open source models. For us, we use Clip, VQGAN. We actually use the pre-trained BART model that we fine-tuned, and use open source code. And I think, I would say like in Hugging Face, you have a training script for everything, and it's actually true. In our case, we based it on a summarization model that was already existing. And you start with something that works, and you see, can you make it run? And you slowly update it based on your needs. And you slowly add more complexity based on what you want. But don't start everything from scratch. Start with something that works and little by little modify it, because that will be way easier. It's important to have a good baseline and a first prototype that works. A good resource also is like if you go to Lucien Rain's repos, whatever paper exists, he pretty much has a repo for it. So you will find some good inspiration in it. Also, they are really well documented. There's a really nice README that explains quickly how it relates to other papers. So it's a good reference. I'm going to talk quickly about DALL-E Mini now, how it works. So basically, we have a sequence-to-sequence model. Here are the inputs. For example, it would be a sentence in French. And here are the output, and it could be the sentence in English. So here it would be a translation model. Sequence-to-sequence are often used for translation or summarization, something where you first get a sequence of inputs, and then you get another sequence in output. It's not the same structure as DALL-E, so here we were like a little creative, because DALL-E, they have the entire sequence in one, all concatenated together. So you have the text, then you have a special token that tells you, okay, now I'm starting to output the image. So you can do things a bit differently. It's good to see like, okay, can I use that type of model, and can I apply it to my specific problem? And here is the architecture of DALL-E Mini. So what's interesting is like you have a caption, you have an image. The caption goes to a BART model. So BART is sequence to sequence. So you get that sequence of text that is tokenized, that here becomes just a sequence of discrete inputs. And then on the other side, you have the image. You use that thing that we're going to look at what it is, but it's a VQGAN encoder. It's an image encoder, basically. And its goal is like, my image, I'm going to transform it into a series of discrete tokens, so of discrete numbers. And then I'm going to try to go from one to the other. So here I'm going to try to get my input of text tokens. I predict what would be the image tokens. And I just have a cross-entropy loss to compare to what is the ground truth. I'm going to go a bit into more details on that, but these models are not used a lot for some of the diffusion model, but they're used actually in Party, for example, uses the same principle. You also have Muse, it uses discrete tokens. So it's very interesting that it can still be applied in some of the recent state-of-the-art models. And once you have that, the inference is very easy, because you give your text, you output a series of tokens which correspond to an image. So you had your VQGAN encoder, which goes from the image to the tokens. You have the reverse transform, basically, which goes from the tokens back to an image. And what we would do on those, it's optional, but we would rank them with CLIP. CLIP is a model that tells you how good your image matches a caption. So then it can select what are the top ones. It's really optional, but it adds a bit of quality when you have like noisy outputs or outputs that don't really match the model. So it's a multi-modal. It's multi-modal, and basically you try to maximize the cosine similarity between text and image. So you encode text to a certain embedding vector, you encode an image in another embedding vector, and then you just multiply them together, and you want them to be as close as possible when they are normalized. And that's what will put the embeddings together. CLIP is used, by the way, for other applications. It's also used for stable diffusion. They use the text encoder of CLIP, so it's very powerful model that gets understanding of text towards images. One of the steps we had, which is one of the mini steps, was fine-tuning the VQGAN. So the VQGAN is the image encoder. What it does, I'm going to go very briefly on it, but you have an image and you try to transform it into discrete tokens. So you have a variational autoencoder, but at the bottom of it, what you try to match the embedding to a codebook that is discrete. And using losses in a smart way, you get that to train, and you get that to have a finite numbers of codes that correspond each to kind of a patch. So one of these numbers, for example, 94, could mean, okay, it's a green patch. 33 could mean it's a yellow patch with a red dot on it. It's a bit more complex than that, because in the end, you have a convolution applied on it, so they all kind of interact with each other, but that's the base idea. And the GAN part of the name is based on the fact that the original model is more like a VQVE by OpenAI. So when you do that directly, what happens is your image can be a bit blurry. Your encoder tries to minimize the loss, so you have a bit of blurred details because it tries to minimize a squared loss. But when you add the GAN loss to it, what it will have, it adds more details to it. So VQGAN, that's what they do. They add a GAN loss to it, and you get a bit more details, which translates some more quality, I would say. So we fine-tuned it, and I'm going to go really quickly to it, but it was not very good at faces because there's a lot of options of VQGAN we could use. And we used the F16, which compresses the image much more. The reason is, like, at the end, we wanted just a model that works. F16 compresses it more, and it's fewer tokens. That means it's faster to train. At the end of the day, we don't have much time to train. So I think it was a good choice. It was hard to train at the time on TPUs because some of the operations that were in the PyTorch code were not supported. In the sprint, you're going to use JAX code, so everything works perfectly. You don't have to worry about it. But we ended up renting GPUs to try to fine-tune it a bit more. At the end, I think we used that one, but I don't think it improved that much the VQGAN. It was actually a challenge. What's important, when you have a roadblock, it was not essential. We used the pre-trained model, so we had pre-trained model for a lot of the parts of the pipeline. This part didn't work, but was not essential. It's important to move on. So one of the person was on it. That was me, and it didn't work that well. We still used it, but then Tanishq, for example, tried to see if we could make it work on TPUs to fine-tune it a bit more. But that's why it's important to have many members, and work on those tasks that are a plus, but be able to move on and work with something else in the meantime. Preparing the dataset is a big part, so I would say, try to prepare them early. Have 1 or 2 members of your team work on it. You don't want your dataset loader to be the bottleneck, so you need to try it. Test also, loading your data and reconstituting the images so that you get what you have. For us, we use the web dataset format, which is fast and efficient to encode the images. And when they were in token, we use Hugging Face datasets for it because of all the convenience functions that are there. So the prototype now, this is the fun part. I'm going to go a bit to the code. What we did, we looked what was the most similar, and so we have that BART model that goes from a sequence to another sequence. And there's already a model in the Hugging Face library that can do that. The main difference for us is we want to separate the encoder tokens to the decoder tokens. Typically, you summarize, maybe you have shared tokens between the two. We need a few adjustments because we're gonna use our image tokens, but it's basically the same model otherwise. So what's fun, maybe some people will find it's a bit dirty, a bit hacky, but we import the FlexBart module from the Hugging Face transformers library, and we just override it with another module. So we do class FlexBart module or FlexBart module, and here we just change the setup method, and that's all we did, and that was pretty much our model. And then we have a few other models, over time where we changed things. So I can show you, the latest version of the code quickly. But if you go to the Lamini over time, I did a lot of other methods, and there's a lot of still import from the transformers library. And if I go to the modules, you see like FlexBart attention, since it still inherits from a module that's from Hugging Face, and I just overwrite whatever methods I want to change. And I go to FlexBart module, and I still overwrite some methods. And I think, you can just copy paste also and modify it. Just I wanted to benefit to what other updates they would do, but things break sometimes. So there's pros and cons. So we did a quick model sizing because there's different models there. So we saw like what can fit in our architecture, what can fit in our TPU. At the time we used TPU v38. Nowadays you have v48, which are even better. And you want to first check what is the max batch size you can fit in memory. Typically, the bigger batch size, the better. There's no reason to have a small batch size anymore. Depending on your data set, obviously, if you don't have much data, sometimes it changes. But then, you want to do some gradient accumulation, maybe to see if you can fit only a small batch size. Let's say you can fit only 100 samples, you're going to do gradient accumulation and look at in the applications what are typical batch sizes that are used, and try to match it or be as close as possible to it. It will help your model train. If the batch size is too small, it won't work really well. It's important to do a search of learning rate. There's hyperparameter optimization. There's tons of parameters you can optimize. If you optimize one, I would say the learning rate, spend time on it because it changes a lot of things. We spent one day to optimize it, and you see we did a quick search. We did a few experiments. Khalid was running on the experiments on the different TPUs, and he found one that worked the best. And then we have only 3 days left to train our model. So we're like, okay, it may be time to train our model. So we start training it. And as we train it, even before we trained it, we had also some people in our team. Tanishq was working on that, working on having a demo to experiment, is it training correctly? Because you train the 3 days and you notice it doesn't work, you're going to waste your time. You can prepare immediately a pipeline to how do I do inference on it. And it lets you find issues quickly. So for example, initially we had little things, the image didn't appear to be right, but then it was our generation pipeline that was not completely correct. But quickly we were outputting aerial view of the beach during the day and during the night. And we had those little blobs of images which were not really correct. They were really like random blobs. But what was cool is like the image by night was kind of dark and the image by day was pretty light or was lighter. So we thought, okay, maybe the model is training, maybe it's doing something good. It was a bit after one day. We're going to see quick examples, but it's really important to implement a pipeline early. Don't keep it for the end. It doesn't have to be your fancy final demo. You can just use a notebook for development. It's great. Use a collab or regular notebook, and everybody can develop and work on it. and play with the model, but you need to do that early on. And then when you want to do an app that everybody can use, Gradio is pretty convenient for that, because once you have your pipeline, the interface is built immediately. So I would say, it's important you start with a pre-trained model if you have one, so that you benefit from its knowledge and you get results quickly. Maybe you can freeze some weights based on what you do or not. But this is what we would get after an hour. So as you train, as you implement your pipeline, you want to monitor the progress. You have the fancy way of really logging your samples, and then you can see the evolution, but at least observe them manually in the worst case. So after 1 hour of training, this is what we would get: a farmhouse surrounded by beautiful flowers. I'm like, okay, we're getting some kind of images. So hopefully it's doing something, but it's kind of suspicious still. You're like, is it really learning something, right? And after 5 hours, we get blobs that start getting shape. And if you're imaginative, you're like, okay, I'm getting the sky in some of the images. So it seems to be working. After 15 hours, it has improved a bit. You see some trees maybe. So you're like, maybe it's working. And here is after the 3 days, basically. And you can see the houses, you can see the flowers, you can see the sky. So that's when it works, and that's when it was cool to see that. So I'm gonna quickly conclude, but basically at the end the TPU died because it was the end of the competition, and our validation loss in the last day was still going down pretty nicely. So like, oh, that would be cool to train it a bit more. We stopped the training early, and who knows what the model could have been. We have very promising results. This is the sunset over Green Mountains, the Eiffel Tower on the moon, the armchair of the avocado, the farmhouse surrounded by flowers. Really great results. And we were like, okay, let's train longer. So after that, I tried to train it longer, and turns out that it didn't improve. Actually, the TPU died at the perfect moment. It started overfitting. We had a small data set because we had little time to prepare it. There was not that many cool resources to prepare it, and limited amount of memory. So I increased it. It didn't really improve. So that's when I was, okay, let's go to 1 billion. And 1 billion model started to look pretty bad. So that's why I'm going to end it, but then started the second part of the story, which is like building Crayon and how to solve it. And, it was about the main things, like you go deeper, you start from that Hugging Face training script, Hugging Face model, and you slowly dive in and you get an experiment that works. And then you have new ideas, you get into new params, but you want to try and you get excited about this. And I think it's really fun event, and I hope you get a lot of fun and learn a lot with it. All right, and that's about it. So now if anybody has any question.
Thank you so much, Boris, for this presentation. It was really fun to see how it all came together and how it all started with this competition. And it's also important to emphasize this happened in the middle of 2021, right? So this is the text to image process, right? And all the amazing advancements we are seeing now. Like, even if today you look at this and it looks, not that great, at the time it was literally the first time someone was actually able to type a sentence and get an image that looks very much like what you were typing in their hands, because there was a DALL-E 1 blog post, but it was a blog post. So this is also, like, when you place it in time, it's very exciting to see. And also the names that you mentioned, the people that worked with you, if we look back what they're doing now, it's like everyone joined the space and now they're like prominent either founders like you, or they work at Hugging Face like Pedro and Suraj, or they are doing crazy new cool things with the medical stuff like Tanish. So it's really cool to see this whole ecosystems. I have a few questions for you. So Alex asked us, they are working on a similar project with a non-regressive VQ sampler, and he's asking if you have any advice regarding training the final model and hyperparameter finding.
Okay. So I would say, if you find, it depends a bit on your model, but if you look, you can find some inspiration, I would say, in Phil Wang model, like Lucinda model, or other models. I don't know exactly what you're trying to do. I guess you're trying to do a model maybe like a Muse. So for the final model, I would say it's always good to start with a smaller model to see that it works, because the long model takes maybe a long time to train, maybe several days. So you don't get much feedback on your model, or is it training well? And you may wait a long time and not get any result. I always like to try to start with a small model, depending on your setup, maybe 100 million to 500 million parameters, which is already quite big, but it lets you see that the model trains. And often when you start with a smaller size and you go to the higher size, the parameters transpose pretty well. So finding a learning rate on a smaller model and then going to the higher model, it's good, because the best learning rate won't be too far off. There's fancy methods to have a learning rate that port well to larger models, but you don't need them. I don't really understand them. Many times I tried them, but often, when you multiply the size of your model, let's say by 3 or 5, maybe up to 10, often the parameters don't change too much. I would say the main parameters that will matter are the learning rate. What for your optimizer, you use the default, it's fine. Whatever default your library gives, or look at other implementations and use their default. They find the default that worked well, and or look at the paper too. They had the time, they did the research, they did a lot of experiments. Use their parameters, and if you want, after that, you can play a bit with some. But the main one is the learning rate, and weight decay, all that is always tricky. Me, I often don't use it too much. Dropout, the same. I don't use it too much. Yeah.
Cool, thank you so much. There's another question from Alex, actually interested in the Cryon follow-ups. So he's asking, can you share any architectural differences between DALL-E Mini that was on the Sprint compared to the most recent Cryon versions? He loves the name, by the way.
Thank you. Yeah, the difference, like DALL-E Mini is more like a BART model, and it uses discrete tokens, and Cryon, the recent version, is more like a diffusion model. So it's a bit different. It would be closer to what you see in Stable Diffusion or Imagen or DALL-E 2. They all use like diffusion. So that's when you have an image that you slowly denoise. You add a little bit of noise and you try to remove it, and you do a few steps. DALL-E Mini predicts the image in one just in one iteration. The only problem is, because it's a decoder model, you have to do one token at a time, so it's quite slow. Diffusion model, you can predict the entire image at a time. There's ways that are a bit in between, like the Muse model, for example, or the VQ diffusion. What they do, they use discrete tokens, but it's a decoder model, so you predict all your tokens at a time, and then you mask randomly some tokens and you predict them again, and you kind of mix that. To me, it's a diffusion, but in discrete space, and it works quite well because you get a bit the benefits of both. So, yeah.
Oops, I was muted. Cool. And then we have a last question from Shish. He asks you, how much of your TPU time were you able to do the final run, and how much was wasted in experiments that didn't fail runs? I think you touched upon it a little bit, but if you could expand on that.
Yeah, so actually this is interesting, because often when you see the time that people train on TPUs, they're like, oh, this experiment runs in a week or runs in 2 days or in 3 days. But I would say the training time is 10% of the actual time. The only things, like, I think when people train on big machines, you first start developing on a tiny machine and then you run on the big machine. But a lot of the time is spent on debugging, on making it run. So the final training run was the last 3 days for us, but we had the machines for, I think, 2 weeks. The entire event was 3 weeks. I think we had them a week in. And, it was understanding how to connect to TPUs in SSH, basic things, initially. But yeah, you're going to experiment in Colab, even in it, and and you're gonna try to make things run. And the good things, you have good starting scripts that will let you run things quickly. But yeah, there's a bit of a headache at the time, or like you bang your head against the wall a little bit, because it just your model maybe doesn't run at all, and this is part of the game. And I think, the good thing is, like, after you bang your head on the wall a few times, just once the machine runs, you're just so happy. You're like, okay, it's training, and it's a really nice experience.
Well, awesome. Thank you so much, Boris, for your time and for your presentation. I think it was inspiring for me, and I hope it was inspiring for everyone that is joining the sprint. And we hope to see many works inspired in spirit by the DALL-E Mini process. And I'm excited about the Cryon V3 that has been teased. Do you have anything to talk about it? Feel free to.
Yeah, no, so it's the new version is released in a few hours. So excited about it. I think people have been testing it already and like it, and I think it's just fun to see. I just like to see what people do with these models. So it's nice, to let people experiment. To me, that comes back to the first images. That initially with DALL-E Mini, our most creative prompts were like the Eiffel Tower on the moon or a cat with a hat. And then you let people use it, and you realize that the explosion of creativity is really nice. And me, I like a lot the meme prompts. There's a lot of artists that do the nice images, and I like that. But I like also the crazy prompts, the funny things, see what the model do. So I hope people enjoy the new version too.
Awesome. Yes, I think DALL-E Mini was a meme machine that is still unrivaled. Like I mean, all the other image generators are pretty fun, but the meme vibe that DALL-E Mini was able to provide, I think, is still unparalleled. And I sometimes go back to Cryon to like generate. And also, I think the 9x9 grid is a powerful aspect, because sometimes the images are complementary. I've seen many people like you type something and then one image has like you have two people fighting, and then each image has them and they are kind of facing each other. So it's kind of like the randomness of the process helps with the mimetic process as well.
Yeah, that's true. There's that one problem that's funny. Like, people put wiki how, and they type something crazy. Wiki how to save a cat that is becoming a demand or whatever. And what is nice is, like, each one has you have the 9 grid, and each one, it builds a story together almost. While the images are independent, you have kind of a story with the 9 images. So yeah, it's fun.
Cool.
Right. Thank you very much.
Thank you so much. See you soon. Bye. All right. So our next talk will be by Margaret Mitchell. If you followed a bit of the news, you would see that she has been elected one of the 100 most influential people by the Time magazine. And basically, she has an interesting position in that process, because she's in what the Time magazine called a third field that is neither utopian nor super dystopian. This AI will change the world, either for bringing the utopia or destroying the planet, but actually nuanced view, or a view that is focused on what is here right now. But she can tell you way more about that than me. So I welcome you, Margaret Mitchell.
Hi. Do
Hello.
people see me? Hi. Do people see me and hear me? I'm not sure.
I think so, yes.
Okay, great. Cool. So if I can present, we haven't had a chance to run through this, but if I can present, then I can go through my slide deck.
Yes, so feel free to, you can just share your presentation, and I can bring it up into the stream.
Okay. Let me see here. Share screen. Application window, Opera tab. Okay, let's try this. How does this look? Does this look reasonable at all? Or is it like filled with lots of tabs?
No, it's just a presentation, so this is
Oh,
perfect.
it looks good?
Yes.
Awesome. Cool. Well, thanks for having me. Yeah, thanks for arranging this talk. I was hoping to maybe shed a little bit of light on ethical aspects of the text to image generation work. I think probably a lot of people are aware of at least there being some kinds of ethical issues. But I thought it would be useful to kind of summarize what the space is, what kind of issues the space is hitting on, and some of the kind of priorities at play.
Awesome. I'll let you to it.
Oh, okay. Should I, am I being recorded right now for the talk, or?
Yeah, you're live on YouTube, and this will be
Cool.
Yeah.
Cool.
Available afterward.
Okay, great. Cool. So at this point, people are mostly familiar with how organizations and companies put out all these different principles or values that they use to define their work. And that's actually one aspect of what it is to operationalize ethical AI work. It involves identifying different values at play in every decision in light of current and foreseeable societal impacts. So for example, many orgs have narrowed in on things like transparency and bias. In the ethical AI image to or text to image generation space, some of the sort of concerns, values, and priorities start with C. So I like to try and think of things that might be a bit more memorable for people. So in the text to image space, we can think of the C's of creativity, copyright, credit, consent, and then the overarching paradigm that we're in of capitalism. So I'm going to go through each of these a bit, hoping to help make folks aware of some of these different nuances at play. Cool. So the first AI-generated image that was sold for auction was created using a GAN, and this was in 2019. It's this picture on the left here, portrait of Edmund Bellamy. And the response was mixed. At the time this work was put forward, it was very new to be able to show off this kind of AI art to the art world, to the finite world, and have it be taken seriously. And people were nervous about it, but also excited about it. And one of the interesting things about this release was that the framing on what the image was it was created by the system. It was the AI system itself being creative. And that created some issues in how people sort of approached, created some issues in how people were like willing to engage with this kind of technology, because then it started bringing up the issues of like sentience and consciousness, right? So like, can an AI system be creative? I'm going to break that down a little bit. But basically, it was clear that more and more artists were finding ways to use GANs as tools for text images. So these were people who were able to think about things artistically, whether or not they had formal training, and use these as essentially as tools to create art themselves. Shortly thereafter, another artwork from Mario Klingemann was this Memories of Passerbys 1. That's the thing on the right. And it generates portraits, again, with GANs, and it was sold at a Sotheby's auction. In both cases, the artist ended up pointing out that while the systems create things, sometimes in new and interesting ways, the systems don't do this with intent and without a sense of what's relevant. It's the human, the interpreter, who views and comes up with the meaning. One thing that Klingemann said was that it's like making a fire. You can make a fire and it produces interesting shapes. But in the end, the fire isn't created. It's you hallucinating shapes and seeing patterns. AI is a glorified campfire. So a sort of interesting split between the artists on the one hand, who were seeing this as a tool and something that they were using in order to generate art themselves, and the way it was talked about in more popular culture, which is that the system itself was created, essentially erasing the role of the artist who put it together. And I think this caused a bit more of an uproar than it would have if the AI was talked about more like a tool. More recently, diffusion-based models have become the leading approach. That's why folks are here. And it's further fired up the debate around art and AI. So this work, which is on the right here, is called Theater the Spatial Opera Theater. It's the English translation. And it took home a blue ribbon at a Fairs Context. And a lot of people ended up complaining that this was essentially cheating, right? So artists became more and more nervous about their own futures. Why would anyone pay for art if it can just be generated? And this also brought up a lot of the ethics of AI and AI art generation more and more into public consciousness, where one of the concerns was that systems that can do this are essentially a high-tech form of plagiarism. And you can see I just copied one of the many responses from artists responding to this work, saying that part of the value of art is in the process, not the result. And art has no value if the artist can explain the process. Other people have complained that this art is not grounded in a societal context, and to be real art, it has to be grounded in societal context or human experience. But either way, it's sort of either way, it's clear that this technology is doing something that's incredibly remarkable, and it's creating very sort of fierce emotions, both on the pros and the cons of its ability to do this kind of thing. Okay. But actually, it's fun to think about this because you can go back in history and see that this kind of thing has played out before, and then actually learn from that in order to inform what you can do moving forward. And also, like, it gives you some foresight about how concerned you should be about different kinds of things. And so there was a lot of controversy, for example, when cameras were first introduced and still photographs. So a lot of painters at the time, so this is like late 1800s, when still photography was first introduced, they really recoiled at the idea. They saw it as a debasement of human artistry. And then we have some nice quotes here, one from Baudelaire, who calls it the refuge of failed painters, too ill-equipped or lazy. And that photography is invading the territories of art and has become art's most mortal enemy. And then a similar, I should say, a different view on the same sort of topic was put forward by D. Levine, who said the free availability of the idea doesn't result in a collapse of the market available to the original innovator. A lot of what's going on here with text-to-image generation is similar to what happened with this fear of photography taking over, where artists who had put their heart and soul into creating, physically creating these different kinds of images, felt that now there was this other thing that could only make everything worse. But instead, what we saw was that artists picked up cameras as another form of art. It became a tool for the art that they were wanting to create. And then we were able to develop further kinds of things like licenses in light of modern photography. And so we're probably going to follow a similar sort of trajectory in the development of text-to-image. Cool. So one of the concerns is around the people who have been input into the training, their data. And the fact that the norms of copyright and consent and credit aren't very clear. They're not well defined yet. So the justification that's used most often in the generative art world is that you can use these images because they're covered in the US by what's called the fair use doctrine, which aims to encourage the use of copyright protected work to promote freedom of expression. So when deciding if something is fair use, there's a ton of different considerations. And so there are two factors that are particularly relevant to know about. One is the purpose or nature of the use, and the other is the impact on the market. So there are priorities around whether the use case changes the nature of the material in some way, which is usually described as a transformative use, and if it threatens the livelihood of the original creator by competing with their works. And it's that latter aspect of fair use doctrine that is increasingly now part of ongoing legal discussions. Considering this, it's much more likely than not that the training systems on copyrighted data will be covered by fair use, but the same can't be said for the generated content. And one of the areas where we can learn from as well here is around music and the music industry. One of the high-level takeaways from the discussions of copyright here is that if the model is trained on many millions of images and used to generate novel pictures, it's unlikely that it constitutes copyright infringement because it's not putting any particular artist out of business, right? The training data has been transformed in the process. The output doesn't threaten any market of any specific original art. But if you fine-tune that model on, say, 100 pictures of a specific artist and generate pictures that match their style, an artist would have a reasonable case against you. And indeed, that's starting to happen. I want to talk about something else that I'm worried I don't have a slide for. So I'll just say that there are other alternatives, and I'll get to those next. Okay. So one of the ways that the artist's work interact with ethics here and the law is around their use of copyright. And I think copyright law is really misunderstood, but essentially there's this idea that if a piece of art is copyrighted, then it may be illegal in some way to use it. Fair use doctrine sort of argues against this and says if it's transformative, then it doesn't matter. But one thing to know about copyright in particular is that your work is under copyright protection the moment it's created. So you don't need to register something for it to be copyrighted. It's copyrighted as a function. It's copywritten as a function of you creating it. But then if you ever want to pursue legal recourse, you have to have it already be registered. So this is why people do it. But in general, it's sort of agreed that that copyright exists for the images that are on the web, whether or not there's an explicit copyright associated to it that you can see, or that's been registered somewhere. And still that these images that are copyrighted are still reasonable enough to pick up in training if there isn't any one image or one artist who's overrepresented. And then the issue really comes into play with copyright when it is art that is specific to an artist or some specific style of an artist. And this has ended up creating some kinds of lawsuits. So there are two lawsuits right now to be particularly aware of in this space. The one on the left is this Buttrick lawsuit, which is making the case that AI image generators are 21st century collage tools. And so they are comparing the generated images to collages and trying to talk about how and how that like provides some sort of parallels in whether or not this kind of work can be done. That relies on this idea that the individual pixels that are represented in a text-to-image generation system are somehow connectable to an original image source. There's, I think, a little bit of debate about whether this lawsuit will actually hold much ground, in part because it does seem like the fair use doctrine would override, the concerns that are in this lawsuit. The other lawsuit is much more serious, or I think experts think is much more likely to have a significant effect, and that's from Getty Images. And basically, Getty Images was able to show this other kind of generation where it's tied to some specific artist or some specific style. And here, the specific artist or style is Getty Images, as can be seen through the use of the Getty Images logo, right? So this is this position where it's not the fact that the image is generated from other people's art. It's the fact that it is mimicking some specific style or some specific organization in this case. And that's when the copyright issues really come into play. Most recently, there's been some advancements in how this works. So copyright law is now updated to say that the output of a system can be further copyrighted if there is a lot of additional human work at play. So previously, it was thought that maybe it wasn't possible to copyright anything that came out of a text-to-image generation system because it is a collection of all these other people's works. And it's something that comes out of a mechanical automated process. But as more and more artists have begun to really use this as a tool, use text-to-image as a tool, it's become clear that the artist's work there is copyrightable. So did someone say something? Okay. So to the extent that that original artwork can come out of using text-to-image models, the human artists that create them can, to some extent, copyright that content. But outside of the legal doctrine of copyright, there are some more personal or social values at play with respect to how to recognize others' work. And that is consent, compensation, and credit. And so one thing that's really interesting is that depending on whether or not an AI system is talked about as a tool or an agent, really affects how people see the need to credit all the people in the pipeline that lead to a generated image. So you can break apart the players in some AI-generated content as the crowd. So those are the people whose data is mined. The technologists, so that's like us, I guess these are people who train the model. There's the model itself. And then there are the artists who use the model to create new art. And depending on how you talk about AI, the public perception of who deserves credit fundamentally changes, even for the same kinds of images. So the way we talk about AI really, really matters when it comes to how we realize these kinds of ethical values that are of particular concern. And what credit means is naming people alongside their shared art. And the issue without credit is that it can create marginalization and erasure. So in the case where you have a text-to-image generating system that's generating images much like some particular artist or organization, that means that they become less and less relevant as this other work that is like them but much cheaper is able to be used, and then with time sort of disappear from the public consciousness. So it's really important to give credit when it's the case that a specific artist or style is being copied. And one way that people can actually ask for credit or have asked for credit in the past is via Creative Commons licenses. So this is something I think most people are probably familiar with. You see it all the time. It says CC BY. All these Creative Commons licenses, there's a bunch of them, CC BY SA, CC BY SA NC, they're all sort of like different variations on whether something can be commercial, shared, this kind of thing. But they all actually require attribution. So this is sort of a weird, and has been a weird conundrum for big data, where on the one hand, you should be able to grab up all this data as part of fair use. On the other hand, they have licenses that explicitly ask for attribution. And then what do you do when you put it through in a system where you have actually no way to give this appropriate kind of credit? The thing about Creative Commons licenses is that they're largely developed in a different time, right? They haven't been developed with the idea of how machine learning works. They're still sort of stuck in this paradigm where you have one image and then that one image can be shared other places, and that's sort of it. There isn't the sense of like this mass collection. And so that means that a lot of the licenses that are available now aren't super perfect for what people would actually like. And so we actually need to create new kinds of licenses in order to address these sorts of issues. Credit is inextricably linked with consent, which concerns whether an artist is okay with their content being used. So we can talk about these legal doctrines of copyright, of licenses, but underneath that, the sort of spirit of that is around the consent of the artists themselves. And so I think it's important to be aware that there's actually lots of kinds of consent. And if you want to respect the fact that some artists do want consent, then you can play around with these different kinds of mechanisms of consent. So consent can be opt-in or opt-out. Opt-in is where you say, yes, my data can be used. Opt-out is where you say, I don't want my data to be used. And that's something that Spawning has been doing, the Have I Been Trained system. And there's a bunch of different kinds of consent beyond that. So there's explicit consent, and that can be contrasted with implied or passive consent, where because you're participating in something, you're said to have consented to it, but that can be sort of, shaky legally. And then there's informed consent, which is particularly valuable when trying to ground on, people's different values and what they prioritize. So this comes from a tradition of autonomy and self-determination common in medical work. And it's basically the act of obtaining consent after informing an individual of all the possible outcomes. I'll talk about that in a little bit in a second. I want to also hit on this idea of continuous consent, which is that every time a subject's data is used, they consent again. I don't know that there are any mechanisms for that, but that is something that has also been developed in the medical domain that can be particularly useful for thinking about consent mechanisms. And I also want to flag what I've called forced consent. This isn't actually a term that I've found people to use. It's one I've made up, forced consent. But it's a situation where alternatives exist, but the individual is only given one clear option. And so an example of that is in airports. It's quite common now to be going through a line and suddenly like facial recognition is going to be used on you. It turns out you can opt out, but generally the signs that say you can opt out are off to the side. It's not very clear. The people running the face recognition definitely don't tell you that you have another option. Everybody is trying to go through this line and trying to do it quickly. So there's a sort of peer pressure to just get it done. And so this is what I call a forced consent, where basically there might be some other option, but you're really not made aware of it. And the situation is one where it can be too difficult to really do otherwise. And so this is just sort of a way that consent can go poorly, even if you want to have some kind of opt-in or informed consent without giving people, possible alternatives. Then you get them into a forced consent sort of situation. But informed consent in particular is really useful to know that this is exactly what the person is okay with. So it's probably like the highest level of like a value-informed consent. So it's an ethical and legal doctrine based on the assumption that all interventions, and this again is from the medical field, should be performed after a patient or research participant has been informed about the purpose, nature, consequences, and risks, right? So they're given like this full scoping. And it also includes the right to withdraw. And that's an important aspect of this informed consent doctrine. I think I went the wrong way. Cool. And so some things we can take away from this informed consent kind of doctrine are these general categories. I found one person who summarized it as PARC, the recommended procedure, the reasonable alternatives, etc. I broke this down above in terms of AI a little bit. So in the medical domain, one of the categories of consent is the diagnosis. Applied to AI, that would be something like the intended use. Another is the nature of the proposed procedure. In AI, that would be something like how the model or the application is created. In the medical domain, it includes the risk, consequences, and benefits of the procedure. You could say something similar in AI. Instead of procedure, it would be application or model. An assessment of the likelihood that the procedures or for AI application will accomplish the desired outcomes, and any reasonable or feasible alternatives, including opt-out. So informed consent is a relatively thorough way to work with people's values around consent, even if there isn't a specific legal doctrine requiring it. I think I'm almost at time, actually. So I just have a couple more slides. The notion of informed consent has further sort of blossomed within the digital world or within digital AI ethics work. And there's this project I think it would be useful to be aware of called Consentful Tech, where they're trying to sort of define what good digital consent could be. It definitely borrows a lot from the notions of informed consent. It also includes this idea of being reversible, which is often missed. The freely given, that's similar to mandating that it can't be a forced consent. So it can't be the case that you can only use this system if you consent to have your images used in this way, and you're really not given an option otherwise. It has this additional idea that it should be enthusiastic, which I think is quite ideal. It would be really awesome if everyone just enthusiastically consented to things, but I think even like unenthusiastic consent is probably okay as long as it's consent. But I think it's cool to see these examples of projects that are really trying to hit all of these really important values, kind of like maximizing how many good things they can do in one. And this is obviously particularly relevant in this kind of domain. And just for my last slide, I'll just give another plug here for spawning, where they're playing around with these opt-out mechanisms and will soon be playing around with opt-in mechanisms. Most developers actually do want to be able to respect consent if it's there. And so this work coming out of spawning, I think, is a really useful path forward for playing around with opt-in and opt-out consent mechanisms. And in the future, maybe we can go to even more informed consent mechanisms. Okay, cool, thanks.
This was an amazing presentation. We do have some audience questions, if you would be okay to taking them.
Yeah, of course, yeah.
One is from Kamenduru, and he says, "Hi, Margaret, we have ControlNet. We maintain full human control over AI-generated art with ControlNet. Does it mean that the art creation process using ControlNet is copyrightable?" By the way, just for the record and for this call, even though like this event is not legal advice, I guess that's important to say.
It's really important to say that.
Yeah, so please don't take this event as legal advice. We are not lawyers, but we are talking about the issues as they come. But yes, so.
Yeah, it's a really good reminder. I mean, I'm approaching this as a scholar of of AI, and so studying ethics and law kind of goes hand in hand. But yes, I can't give legal advice. What I can tell you, Kamanduru, is that the Copyright Office in the US has made it clear that it really is case by case. So for any particular piece of generated art to be copyrighted, it must be the case that there has been a large amount of human work on it, and it's that human work that's copyrighted, not the image directly. So it's a kind of tricky situation where it's like something on top of the original piece of art that's copyrighted. It's the human nature of it. So like the way that images could be placed in a book, for example, that's something that's copyrightable. Yeah, there's no easy answer to that, Kamanduru. It's really a case by case basis, and how much the people working with the images are actually putting their own artistic thought into it.
Yeah, and just to add to that, I think there is a concrete example from what you said, which is someone tried to copyright a comic book, and then the comic book image arrangement placement was considered copyrightable, but each Midjourney generated image was not. So the arrangement in the page, the dialogues, everything was copyrightable on top, but each individual image generated by Midjourney was not. However, I think it's interesting because ControlNet adds like human control, like you decide which pose you want the image and stuff. And I think it's actually, I would encourage someone in this sprint, if they generate a cool thing with a ControlNet, to actually apply for copyright registration in the US Copyright Office, describe the process thoroughly and see, because I think there hasn't been yet one like this. So it would
probably make the news. If you do it, you'd probably be making the news.
Exactly. So if someone wants to try to do that, there is a fee. So yeah, you have to be really invested in doing that, but it could be an interesting one. There is another question for you, and it is by Shish. And they're asking, you seem to be saying that if we fine tune a model on the style of an author, the model itself might be infringing. Since this is not in the code, is there a case law to support it?
So I'm not aware of the case law for this, and one of the difficulties with all of these discussions is that there isn't a lot of case law. There isn't a ton of precedent for AI generated content. That said, I don't think I said anything about the model being infringed. Most of the stuff I've read, again, not being a lawyer, or the model being infringing, most of the stuff I've read is about the input and the output. So really the legal discussions have been around the copyright and licensing on the input images, and then the copyright and licensing on the output images. What I was talking about with the fine tuning is that the output of the fine-tuned model that mimics some other artist, that output can be subject to lawsuits, to legal concerns. And in particular, I pointed out the Getty Images example, where it seemed like you could see a specific organization that was being mimicked. It was because of those outputs where there was an issue. The model itself, I don't know about the model itself infringing.
All right. Well, thank you so much for your time. I think we're reaching the end of your talk and of this event as a whole. Thank you so much, Meg, and see you in the next time. And everyone that joined this event, I would like to give a huge thank you. This were 3 amazing days with talks by many different folk from Google, Stability AI, Hugging Face. And essentially, the idea was to give you an overview about JAX, about diffusers, ethical side, how to train different models, what to control. And I hope you had a good time looking into these processes. If you haven't already, we already started distributing some TPUs for the event. So go to the description, join our Discord servers. And yes, I will be looking forward to talking to you more. If you would like to keep in touch, you can follow me on Twitter. It's multimodal art, like you see in the image. And we will be posting about the event in the Hugging Face social media as well. So make sure to be looking into that. And with that, I will leave you, and have a great day. And I hope you have an amazing event. Bye, everyone.